Okay. Good afternoon, one and all. Don't tell, sky's the limit when their footprint on the moon. I am Supriya Nayaka, your host for the session. Welcome to Creative Online Talks. Creative is a group of people who are eager to gain new knowledge. Creative means creativity and activeness. To be active, we need creativity. Knowledge Square is our tagline. Sharing of knowledge increases our knowledge. Vision of Creative is to build constructive thinking on various domains. Our main focus on non-textual, non-academic, non-syllabus related concepts. Every Saturday, we organize online weekend talks on the Zoom platform, and we live stream our program on our YouTube channel, Creative GBD. Creative is thankful to all our resource persons for their knowledge sharing with us. Today's talk on launching vehicle technology and reaching moon, where creativity and innovation converges to ignite our lunar aspirations. Today, we embark on a captivating journey that celebrating the remarkable achievement and explores the limitless possibility of space exploration. As we gather here, we cannot overlook the significant contribution of mission like Chandrayaan-3. The ISRO endorsed the explore the lunar surface. In this talk, we have the privilege of hosting an extraordinary scientist, Mr. Sriju Chandran, sir, Group Director, Technology Development and Management Group. I welcome you, sir, and I welcome one and all for today's session. And to introduce today's speaker, I call Divya to introduce our speaker.
Good afternoon, one and all. It's my pleasure to introduce our distinguished virtual speaker for today's event. With the advent of technology and the power of connectivity, we are fortunate to have an exceptional individual joining us from a remote location to share their insight and expertise. Our speaker is a renowned scientist from ISRO who has made significant contribution. Through their virtual presence, we have the opportunity to tap into their wealth of knowledge and gain valuable insights into the launch vehicle technology and reaching to moon. To present this talk, we have Mr. Sriju Chandran.
Thank you, Divya. Over to Sriju, sir.
Yeah, hello.
Yes, sir. Audible.
Yeah,
sir.
I hope I'm audible.
Yes, sir.
Okay. Can I know what is the class or which are the classes in which the participants are mostly studying?
Sir, it's showing all our mixed hetero group.
No,
It's
what I
not-
mean is, what's you mean from first standard to +2 or?
No, sir. No, sir. College level.
College level. Okay, fine. Thank you.
Okay, sir.
Yeah. I'm just sharing a screen. I hope that's visible.
Yes, sir.
The screen is visible. Can anyone give a feedback?
Yes, sir.
Fine.
It's
good.
visible.
Okay. Thank you, madam. Thank you, dear participants. Welcome to this small discussion on launch vehicles and related technologies. I hope most of you might have watched yesterday's Chandrayaan mission, and it's a long journey to the moon. Okay, it has only started. We have only started. We have almost 1 month of various missions, maneuvers, and then a lot of area we have to come in distance we have to cover. But the most important part, one significant part of that was achieved yesterday. That was the launch of Chandrayaan mission. What exactly you have seen? You have seen a launch vehicle lifting off, and then it is, from the screen you would have noticed, it's slowly gaining its velocity, slowly gaining altitude, and finally the Chandrayaan probe is put into a particular orbit from which it will go to the moon. So when you are talking about space technology, there are two fundamental aspects one can say with respect to space or space related technologies. One is the launch vehicle part of it, and the second one is the spacecraft part of it. There is a very important third segment, what we call the ground segment, which helps us to make use of what we do with the satellite. For example, if there is a satellite in the ground, satellite in space, there has to be ground stations to receive the signals from a satellite. There should be facilities to upload the data to satellite. So there are a lot of things in the ground. So one critical aspect, as I have mentioned, is the launch vehicle. So in this talk, we will concentrate only on the launch vehicle part of it. Launch vehicle, generally in common parlance, we also call rocket. So what does this launch vehicle, or a typical launch vehicle, do? I have mentioned that if a satellite has to stay in orbit or a satellite has to be launched, it has to orbit at a particular altitude and a particular velocity. This is very obvious. What can be the altitude? The altitude can be, say, 300 kilometers. Sometimes it can be 400, thousands of kilometers. In certain cases, it may have to go out of the Earth's orbit and it may have to go to Moon, Mars, etc. So in each and every mission, the launch vehicle have got a different role. But very, very broadly speaking, the launch vehicle has to push a satellite with a certain velocity. It has to be placed in a particular altitude. Okay, so basically what you, in a slightly technical term, what we basically do is, we basically give sufficient kinetic energy and potential energy to a satellite. So that's what the launch vehicle do. So in this lecture, we will see the basic technologies involved. Okay, how a launch vehicle works. So this is the first slide. I hope it's still audible. Still visible. Now,
Yes,
what you
sir.
see? Yeah, thank you. So what you see here a particular vehicle. Okay, this is obviously an automobile, not a rocket. Next, what you see a aircraft. You see an aircraft. Okay, and the third is you see a
Sir,
rocket.
first slide we are seeing, sir.
No,
An
no.
introduction to aerospace.
Oh, I think I have moved on to the next slide. Is it the case with all the participants? You are still stuck at the first slide?
Srinath, sir.
Yes, sir.
Stop sharing and again. Now we are seeing, sir, different
Oh.
modes of transport.
Oh, very good. So you are able to see it now, right?
Yes, sir. Yes.
You are able to see the animation also. Now what you
Yes.
see?
It's a aircraft and
Okay.
rocket.
Okay, I think there is a significant lag. Okay, so there are certain animations. I think it's not getting communicated. So I'm just in this particular slide, I'm only showing a car. Okay, only an automobile. Is it so?
Yes, sir.
Very good. Okay, fine. What I'm trying to show is there is an automobile here. Now an aircraft has come, and now a launch vehicle has come. Okay, so what you basically see here are three different modes of transport. Okay, you have an automobile, you have an aircraft, and you have a rocket. So what is the common aspect of all these three? They are basically transportation systems, right? The basic technologies are different, the size may be different, the shape may be different, the cost may be different, but fundamentally all these three are transportation systems, right? A launch vehicle used to transport something, an aircraft used to transport something, and an automobile or a car or something similar is also used to transport something. But the difference is the technology is different, the payload or whatever we used to take it, that is different. There are a lot of differences. But now let us basically try to understand it in a slightly more technological level. Now, one is, how does an automobile function? How does an automobile function? As you're aware, you fill a fuel into the automobile. It can be petrol or it can be diesel. Then this petrol or diesel will be pumped into the engine, and in the engine it will undergo combustion, burning process. And when it undergoes combustion, it releases large amount of temperature and pressure. High temperature, high pressure gases will be released. So this high temperature, high pressure gases will be pushing a piston that, using a simple mechanism, that will be converted as the rotation of the wheel. And then when the wheel rotates, because of the friction between the wheel and the ground, the car moves forward. So this is what actually happens in an automobile. One obvious question is, who is supporting the car? the car is being supported by the road, is it not? Otherwise, what will happen? The car will fall to the center of the earth because of the gravity. This may seem a very stupid question, but you may see that it has got relevance when you discuss the case of an aircraft and a rocket. So a car is being supported by the road. The weight of the car is balanced by the reaction by the road, okay, by the surface. And then the fuel is burned inside the car by taking oxygen from outside or air from outside. So this is how an automobile works. Okay, now you come to the aircraft. So when you are now coming to the aircraft, if you go by the same logic, how does it function? First of all, the weight of the aircraft is, or rather the mass of, due to the mass of the aircraft, the earth is being pulled towards its center, the aircraft is being pulled towards the center by the earth, then how the aircraft doesn't fall down, how the aircraft remains airborne, that is a different technology, right? So the aircraft, if you see, all aircrafts will be having wings. Okay, typically all the aircrafts will be having wings. And what does the wing or what wings basically do? The wings will provide what you call a lift. Okay, we will see that a little bit detail later. So the wings will be giving an upward force, which will be balancing the weight of the aircraft. And then the forward movement will be provided by a propeller. And here also, you take only the fuel, you take oxygen or air from the outside because oxygen or air is available outside. Okay, now you come to the third system. This is the rocket. So the rocket, the same questions if I ask you, how you may be able to answer. First of all, the rocket cannot be supported by the earth because the rocket is flying. Okay, the rocket cannot be supported by the air as in the case of aircraft because the rocket has to go out of atmosphere where there is no air. And due to the same reason, you cannot take oxygen or you cannot take air from outside and burn. So for any combustion process, as I have mentioned, you require an oxidizer. But unfortunately, since the rocket is going out of the atmosphere within a few minutes, it cannot depend on the fuel, oxidizer from outside. So that is why the rocket technology is slightly complicated, or rather much complicated than the other two, because first of all, it has to find a different way of propelling itself. It cannot move, or it cannot fly, or it cannot go up by rotating a wheel. It cannot go up by providing a wing. It cannot go by taking air from outside. So what it has to do, it has to find a different mode of propulsion, number one, and then both the fuel and the oxidizer, it has to carry along with it. Okay, so once you do all this, once you solve all these challenges, you have a working rocket. So this was what I was trying to say in the previous slide. I think now the slide is changed. Do you see any basics of aircraft flight?
Yes, sir. Yes, sir. Drag,
Okay.
lift, thrust,
Very
and
good.
weight.
Okay, fine. So now in the picture, you are seeing a typical aircraft. Okay, so the aircraft has got mass. Since the aircraft has got mass, what will happen? The earth will try to pull it down. You may be seeing now, the aircraft is trying to fall down. Okay, so in order to avoid the aircraft falling down, you had to provide an upward force. This is what you call the lift, right? And then what is the function of an aircraft? It is not supposed to just remain airborne. It is supposed to move forward, right? So any force which gives a forward movement in a rocket or a rocket in an aircraft, it is called a thrust. So these, if you are a college student, studying science subjects, these terms may be familiar to you. The weight, of course, is very obvious, what the force imparted by the earth due to the mass of an object is what we call the weight. And thrust is a force which helps a device to propel itself. And drag is any kind of opposing force which is functioning or which acts against this movement. For example, if you are traveling in a bike, you would have observed due to the presence of air, there will be an opposing force to your movement, right? That is what we call the drag or aerodynamic drag. Similarly, if an aircraft has to remain airborne, as I have mentioned, there has to be an opposing force to the weight, and that should be exactly equal to that of the weight. And then only the rocket and the aircraft will remain airborne. So this term is called the lift. So the lift, weight, drag, thrust, they form a simple cross. The lift will be balanced by the weight, or the lift will be overcoming the weight. The thrust has to be much higher than the drag for the system to move. Okay, so this is how the basic the force balance of the system it takes place. This we call in physics or engineering term as an equilibrium condition. Okay. Now, in order to show this a little bit more detail, if you are a science students anyway, you will be familiar. The lift, that is the upward force experienced by an aircraft, is proportional to the rho, that is the density of the air, A, that is the total area of the wing, and the V, or the velocity square. Or what I'm trying to say is, when the aircraft is traveling with more and more velocity, it will be having much and much lift. Okay. So if you are not very clear, I probably this example may give you a small detail. I mean, it will give us a little bit more explanation. You just see an aircraft in the ground. I hope this is again visible. You see an IL-76 aircraft on the ground. In any case, if you are unable to see that, you kindly let me know. Now you may be able to see. Okay, you are able to see. Fine. So there is an aircraft on the ground. So when the aircraft is standing on the ground, what is the velocity of the aircraft? 0, right? Because the aircraft is just on the runway. And since the velocity of the aircraft is 0, as I have mentioned earlier, there will not be any lift. Okay, but there is still weight, right? Because there is a mass. The aircraft is having mass, so Earth is attracting it towards itself. So there is a weight. So this is what you see. So now, what does an aircraft do in the runway? Does it just take off and fly just like that? No. First, it has to run in the runway. That's why it's called a runway. It will be just accelerating. It will be starting its engine. You would have many of you would have traveled in an aircraft or would have seen an aircraft. So the aircraft will be just moving through the runway. And in the right simple graphs, you can see the velocity is building up. And since the velocity is building up, the lift is also building up. But the lift is not equal to the weight. You can see it here. The lift is not equal to the weight. So what happens? The aircraft remains still on the ground. But at one particular point, you can just see carefully, at one particular point, what will happen? The velocity becomes more than a critical value, and then the lift will be more than that of the weight. And then what will happen? The aircraft will take off. Okay. At the normal flying condition, the lift will be adjusted in such a way that by controlling the speed of an aircraft, by controlling the control surfaces, by controlling a lot of devices in the aircraft, what we basically, or what the pilot basically do is, he will be controlling the lift just equal to that of the weight. So the aircraft is remaining in level flight. Okay. So there is a small error here. The thrust will be much more than the drag, so that the aircraft flies in the forward direction. Okay. When you want to land, what will you do? You reduce the speed. And when you reduce the speed, what will happen? When you reduce the velocity, what will happen? The lift will also fall. When the lift is less than that of the weight, the aircraft will be descending, and finally it will be landing. So this simple mechanism or simple principle of physics is being used in an aircraft. So there are two different things which you may be familiar. Now, one is the fundamental principles of natural philosophy, which we call the science. Right, generating information, generating principles which connects various physical parameters. This is what we generally call the science. The knowledge, useful knowledge, is what we call science. But how do you make use of science to make things, to improve our day-to-day life? This is what we call technology. So there are different aspects of, you can say, the knowledge gathering or knowledge application. One is the science, that is gathering of knowledge, verifying that the knowledge is right. And then you have to test it, and you have to ensure that this is correct, establish clear mathematical relation between the parameters. All these things are basically what we call science or scientific principles. But application of science into making things, making useful devices like aircrafts, rockets, this is called the technology. So both science and technology almost go in hand. Science actually may lead the technology. Once you have a scientific principles, there will be some devices coming up. It can also happen the other way around. People develop something, then the people will find out what is the science behind it, and then further improve it, etc., etc. So this is how the humanity has progressed from cave dwellers to what we are here today. So this is how the systems basically, the aircraft is working. Now, I have asked a question slightly earlier. See, we have seen how an aircraft works, or how an automobile works, or how and what are the basic principles involved. Now, see, for example, here, if you want to go to space, outer space, how a rocket can function? Because I told you it cannot work with air, it cannot work using a wheel, it cannot work using a wing. So how it can be done? Okay, so there is a person here shown. Again, I think it's the slide is visible. His name is Tsiolkovsky. He was a Russian school teacher. His full name was Konstantin Eduardovich Tsiolkovsky, born in 1857. So he has, after a lot of studies, observation, he has made a very, very important postulate, which said, if the human beings or the mankind has ever to leave using, ever to leave the planet, which of course we did much later, it will be based on what we call a reactive propulsion. Okay, there are different kinds of propulsion, that is moving a device from one area to another. This is what we call propulsion. So reactive propulsion will be the method by which a rocket can function. So what exactly is reactive propulsion? We'll just see that. It's very, very simple. So what you see here, you see a balloon. I hope slide has moved smoothly to this slide. So you hope you know, you will be seeing a balloon, right? And
Yes,
in this,
sir.
yeah, fine. So in this balloon, what you basically see, you see a person holding a balloon, and this balloon is filled with the the balloon is filled with air, and this person is holding this exit of this balloon and keeping this exit closed. So if you remove this hand, if he removes this or readjusts his finger, what will do? What will happen? It's very obvious, right? The air will go out, and when the air is going out, because of the reaction exerted by the moving air, then the rocket, or sorry, the balloon will move in the opposite direction. This is nothing but the combination of the second law and third law of formulated by Isaac Newton. What does the second law say? It says the rate of change of momentum is directly proportional to the force, and it acts in the same direction as that of the force. So what is the rate of change of momentum? Mass flow rate into velocity, or mass into velocity is the moment. Mass into velocity is the momentum. Rate of change of momentum is mass flow rate into velocity. So here what actually happened? Here mass flow rate is taking place. Mass is being thrown out. And because mass is being thrown out at a particular velocity, the net force is equal to mass flow rate into velocity, right? So the mass flow rate into velocity is resulting as a force, which is again force mass into acceleration. And because of that, the balloon moves forward. So this is a simple example of a reactive propulsion. So what we have seen, there is a balloon. The balloon has got some captive gas. So this gas is thrown out through one direction of the balloon, and because of the reaction, it goes. Okay, so this is what we call reactive propulsion, because the propulsion mechanism works based on the principle of reaction. Now, let me ask you a simple question. Will this mechanism be effective in space? Suppose if I go to space, in the vacuum of space, where there is a net zero gravity, in the sense the forces are all balanced, will this mechanism work? Okay, this is an obvious question. Surely it will work, because it doesn't depend on anything else. It only throws matter from inside to outside, and because of the reaction, it works. So it is, this principle is universal. It can happen anywhere. It can function anywhere. So the reactive propulsion system can function in Earth. It can function in the atmosphere. It can function outside the atmosphere. So this is the basic principle of a rocket. This, of course, you would have studied in your primary, UP or high school level. This is the basic principle. So another example, which is very familiar to you. So you are seeing a cannon, and when you fire a cannon, what happened? Same thing, because the cannonball is moving in the one direction, the momentum exerted by the cannonball will make the cannon itself move in the opposite direction. So you are seeing in the other photograph also, video also, you can see the cannon is being fired. When the cannon is fired, the shell moves in one direction. Because of the reaction, the vehicle moves in the other direction. So simple mechanism of reactive propulsion. But the question is, can you use this to, can you use a balloon to go to space? Is it possible? Technically, it may be possible, but it's not at all practical. Why? Because the amount of energy released from the balloon is so small that it cannot take anything worthwhile to space. When you're going to space, you have to take some mass, right? For example, Chandrayaan or some satellite, they are thousands of kilograms heavy. So you cannot go to space by the energy provided by the balloon. So you have to go to the next step. So there is another experiment shown in this slide. Maybe you are seeing this, you can see one gentleman's picture here, and there is a device. So what do you see here? There is some kind of a pot, right? And then there is a spherical vessel, and it has got two nozzles pointed in opposite directions, one here and the other here. Now, assume that you are having water inside this pot, right? So I am just heating the water. I am just giving a fire beneath. What will happen? What is actually happening? This entire mechanism is rotating. Why this mechanism is rotating? I think it's obvious. When you heat the water will be converted into steam, and steam will go to through these pipes, will go to this sphere, and then it will be going out of this sphere to the oppositely placed exit or nozzles or whatever. So because of that, because of the reaction rotation. Okay, this is another basic system using reactive propulsion. But here, what is the difference between the previous example and this example? In the previous example, ordinary air was thrown out. The air was not having much pressure. The air was not having much temperature, or the total energy of the gas which is going out was very less. But here it's much, much higher. So since it is much higher, it will be more efficient. But it is not as efficient as we ideally would like to have. Why? There are a lot of issues. First of all, there will be a lot of heat transfer or energy transfer is taking place. No, first of all, the coal or the fuel is converting its chemical energy into thermal energy. Thermal energy is transferred across water. Then water is undergoing a phase change. Then that high temperature steam, which is not very high temperature, maybe 100, 110 degrees Celsius, that goes out. So there is a lot of energy transfer is taking place. There is a lot of wastage is taking place. So even though this is more efficient, or it's having more energy content than the previous example, it is not as efficient as we need. So this is the third example. Okay, so in this case, the fuel and the oxidizer. Okay, as you're aware, no, for any combustion process to take place, the fuel and oxidizer has to be there. Now, why there has to be combustion? I told you, when a rocket has to function, or if a rocket has to function, it has to throw out large quantity of high temperature, high pressure gases. This is required. So how we can produce high temperature, high pressure gases? One simple method or one efficient method to produce high temperature, high pressure gases are by the process of combustion. That is, you take two chemicals, one is a fuel, the other is an oxidizer. Okay, the fuel is and the oxidizer, you are familiar, you are college students, you are familiar. So the fuel and oxidizer reacts, and then what will happen? It will release large quantity of high temperature, high pressure combustion products. This will be at high temperature and high pressure, and when that is getting thrown out, what will happen? It will move in the opposite direction. So this is how the modern rocket functions. What I mean by the modern rocket is, it is a chemical rocket. This may have a fuel, this may have an oxidizer, and both the fuel and the oxidizer will be mixed, and when it burns, high temperature, high pressure gas release, and it will move in the opposite direction. So this is what is happening. And this original concept of this apparently has been done for the first time in China, maybe 1,000 years earlier, maybe 80,000. They have working rockets with gunpowder. Gunpowder was invented much earlier, but people started making rockets around 1,000 AD or so, primarily for festivals and religious purposes, and obviously for military purposes. So this is how we had the basic rocketry. Okay, so what we have seen here is we have discussed about the fundamental technology of rocketry. And as I told you, it all started thousands of years back. People use this gunpowder for many purposes like festivals. And then these rockets were issued in China, and the China was conquered by the Mongols, by leaders like kings or emperors like Genghis Khan. So Genghis Khan got the technology from the Chinese, and when he moved on to Europe, he has used it in Europe. The Europeans got it. And one major historical record of the gunpowder used to rockets are from India. And as you're aware, there is the Tipu Sultan, the Sultan or the King of Mysore, Srirangapatnam. He had used it against the British in the Srirangapatnam War in the 1790s to 1799. So at that particular point of time, this was probably the world's most advanced rockets. That is, they will fill the gunpowder inside an iron casing. Till that time, people rarely use iron casing. So since they have used it inside iron tubes, and more pressure it can withstand. And then because of that, the rocket should go to almost 2 kilometers. And at the end of that, sharp swords, etc., were attached. And since it was attached like that, you can see here. So when these rockets were going, and since it was having weapons at the tip, so when it falls near the enemy, it will be cartwheeling, and then it will be hitting the animals, it will be hitting the horses, elephants, and they will be running amok. So it used to create a lot of destruction during the warfare. So this has happened in India in the around 2 centuries back. So this is one critical technology which India have mastered at the time itself. But after the war, the Britishers have taken the rocket to England. They have studied it and they have improved it further. And many Europeans have access to this technology subsequently. Okay, and people have tried to go to the rockets were not just used for festival purposes. Some people have used it to travel also. Okay, so this is in somewhere in 16th century. There was a Chinese official called Wan Hu, who thought, by attaching a lot of rockets to a chair, and then probably lighting all of them together, he can go to some distant places and probably to the moon. But what has actually happened is these rockets, of course, were very crude, and instead of having a smooth travel, apparently the rocket blew up and he got killed. Okay, so these kind of sacrifices people used to make all along for the cause of science and for the sake of knowing things. And as I've told you, people have taken the technologies to Europe. They have developed it further. It has been used in wars all along. But in the 19th century, till this particular time, people are primarily using the old technology of gunpowder. And gunpowder is also not very energy efficient or very, very powerful. But in the 19th century, there are a lot of new chemicals were discovered by people predominantly in Europe, especially the gun cotton. Gun cotton is nothing but nitrocellulose. And then nitroglycerin was synthesized, and a large number of similar other chemicals. So the rockets, the fuel has been very, very powerful. And there have been people like Tsiolkovsky, Robert Goddard, etc. They all wanted to make use of this these rockets for traveling, for taking people from Earth to Moon, etc., etc. So this is a very bold thinking in the 19th and 20th, early part of 20th century, but they were making attempts to do all these kind of things. And Robert Goddard made the first liquid powered rockets also at the time. We'll see what I'll tell you. We'll skip the history here, or we'll just fast forward. During the Second World War, you may be familiar, the Germans had a very advanced rocketry or very advanced rocket made at that particular point of time under the leadership of Dr. Werner von Braun, who was a very young engineer during the Second World War. He has made the world's first, you can say, true rocket. So it had all the features of a modern rocket, and it had a ton of 20, it has a thrust of 20 ton. 20 ton means 29.8 Newton, kilonewton. So that kind of powerful rockets the Germans could develop in the Second World War, and it had a range of 220 kilometers, which was very, very significant. So the Germans could fire these rockets towards the British Islands from places like Belgium, and this had a weapon or a explosive at the end. So when it used to go to England and impact on places, that used to create a lot of damage. So the first modern rocket V2 unfortunately was used for destruction, but this technology was a very major milestone for the development of rocketry. And as you are aware, after the Second World War, the Germans were defeated. The Russians and Americans, they got parts of German technology. They developed it further. So the history goes in a different direction. But we won't concentrate much on that. So here, now again, we'll come back to the rocket part of it. See, I have just mentioned to you the fundamental principle of the rocket is basically using reactive propulsion, or the reactive propulsion is the method by which a rocket functions. For that, what you have to have high pressure, high temperature gases, okay, developed by the rocket combustion. But one thing you have to be very careful, no combustion process by itself will produce high temperature, high velocity particles, because the combustion will produce high temperature and high pressure if it is contained. But if a rocket has to function, it has to have high velocity, because if the velocity of the mass being ejected is very high, then only you will get significant amount of thrust. Because if you may be remembering, you may be remembering, no, this the mass into acceleration is nothing but mass into velocity by time. So if the velocity is more, you will have more and more thrust. So you have to have the rocket engine has to have high velocity or high speed of mass ejected. But in a combustion process, you will not get high speed, you may get high pressure and high temperature. So how to convert this mass, I mean pressure into velocity? For that, there is a simple device called a nozzle. This again, if you are engineering, some of you are engineering or physics students, this may be familiar. There is a simple device called a nozzle, and what you see here is what is called the convergent divergent nozzle. You can see because of the shape, it's also called a DeLaval nozzle after the person who was first used it for primarily for dairy industry applications. So in the combustion chamber, what basically happens? We have the combustion process taking place. The fuel and the oxidizer will be coming. It will be burning. It will be releasing high temperature, high pressure gases. But the high pressure, high temperature gases will be further accelerated through this simple mechanism. And at the exit of the nozzle, you will get high velocity. Okay, but you are again I hope you are all familiar with what we call the law of conservation of energy, because energy in a closed system cannot be increased or decreased. Just like that, there it only can be converted from one form to the other. So in this particular system, when the pressure is falling, the velocity is increasing. Or in other words, if you want to increase the velocity, the pressure has to fall. Right. So this is application of something similar to Bernoulli equation applicable for a supersonic fluid. So what I'm trying to say here is there will be a device called a nozzle in a rocket engine. The function of the nozzle will be to convert pressure into velocity. So if you see any rocket engine at the exit, there will be a nozzle. You can see a nozzle here, you can see a nozzle here, etc. Now, one important aspect of rocketry and rocket technology is the types of propellants. Okay, I have told you the combustion process is important, and for every combustion, you require a fuel and oxidizer. And there can be different types of fuel and oxidizers, right? That depending upon the nature of chemicals, there can be classification. But one very fundamental way by which you classify the propellants are by using their physical states. Okay, physical state, that is, whether they are liquid, whether they are gas, whether they are solid, etc. So accordingly, you have a solid propellant rocket and you have a liquid propellant rocket. And here, what do you mean by propellant? In rocketry, what you do is the fuel and the oxidizer together are called propellants, right? Normally, in an automobile, you don't generally worry about the oxidizer because oxidizer is available. So you only say that it has to be filled with fuel. The oxidizer is taken for granted. It will be just taken from atmosphere. But as far as a rocket is concerned, you have to fill both fuel and oxidizer together. So in order to make this addressing of this things very simple, you always use the word propellant rather than using fuel and oxidizer always, right? So in a rocket parlance, when you say propellant, you basically mean fuel and oxidizer. So in a solid system, a solid propellant system, what you see here on the left, you have both fuel and oxidizer in solid form. Fuel and oxidizer in solid form will be taken. It will be powdered to a very fine size of the order of microns. That is 1,000th of a millimeter. So why you have to make it the powder? Because again, you are aware from chemistry, more and more surface area means more and more reaction. So it will be powdered to very fine size. Then it will be mixed together. It will be bonded together, and then it will be cast into a particular shape. So as usual, as I told earlier, there is a nozzle at the end. So when the system is started, there will be an ignition command given. Based on the ignition command, some system called igniter will initiate the rocket. It will give a flame, and then based on that flame, the entire propellant within the combustion within the rocket engine will start burning from its surface, and then the high temperature, high pressure gases will be going down, and the rocket will be lifting off. In fact, yesterday, if you have seen the launch, the GSLV LV-3 rocket used for Chandrayaan mission, that's one of the most powerful rockets, one of the powerful rockets in the world, and certainly the most powerful India has ever developed. It has got two huge motors in the first stage, solid powered motors in the first stage. They are similar to what I'm just showing now. And when you have when the liftoff, what you have seen is when the command is given to both the motors simultaneously, both the engines simultaneously, they have the same process of producing high temperature, high pressure gases have taken place. And because of that, the rocket has just lifted off. In fact, the central core engine has not started or will not be functioned or will not be initiated unless it's at a certain altitude. Okay. So the two solid powered rocket engines only lifted Chandrayaan up yesterday. And then it, of course, it has got subsequent rocket engines also, but during liftoff only those were initiated. And now, second one, what you see on the right is what we call a liquid powered rocket stage. Liquid powered rocket stage, as the name indicates, the fuel and oxidizer both are in liquid condition, liquid physical form. Okay, the oxidizer may be in one tank, the fuel may be there in another tank. But if the rocket has to function, what has to take place? Both the fuel and the oxidizer has to be pumped into the combustion chamber. Okay, this combustion will be taking place in a small area here. So fuel and oxidizer has to be pumped using pumps. So pump has to be run by a lot of other complicated mechanisms. So the pump will be driving the fuel and oxidizer into the combustion chamber, and then the combustion will be taking place. Again, the combustion product will be thrown out through the same nozzle, and the nozzle will be accelerating it. And when the nozzle is accelerating it, it will be high velocity will be generated. And due to the high velocity, the high thrust will be developed. And here, when the fuel and oxidizer is fully consumed, which I hope we can see here, the rocket engine will be shut down. Okay. It is also possible to shut it down before that, but this is how it's generally done. So at this particular point, we have basically touched upon the fundamental principles of a rocket. And there is one more term which may be familiar to you. At least you would have heard the name if you are interested in this principles of rockets and rocketry, etc. That is cryogenic engine. I will also try to mention it in using a couple of minutes. So I told you one of the fundamental requirements of any rocket engine is to provide very high velocity, or in other words, very efficient way of providing thrust. Okay. One way of comparing the different types of rocket engines and rocket engine stages are using a term called a specific impulse. I can give you a very rough equivalent. It's not exactly correct, but a rough equivalent will be like a fuel consumption of an automobile, right? You can say that by filling the scooter or a bike or a car with 1 liter of petrol, how much kilometer you can get. So this is one way of saying that how efficient the system is. So similarly here, there is a term called a specific impulse. Specific impulse basically mean how much amount of thrust is generated with the unit mass flow rate or weight flow rate of the propellant. Okay, so this is a good performance indicator. So the solid propulsion system may give you something like 280 to 300. Some other liquid propellant like nitrogen tetroxide, UDMH, they may give it slightly in excess of 300. And some other LOX RP1 semi-cryo systems will give something like this. But people have found out from chemical analysis or chemical equilibrium studies that a combination of fuel, a combination of hydrogen and oxygen will give you very high specific impulse. You can see, right? So the most efficient fuel and oxidizer combination, which is practical. Of course, there are something else like fluorine, but it's not very practical. Practically, if you want to have very high efficiency, you have to use hydrogen and oxygen. Very simple. But one small problem is there. The hydrogen and oxygen are gaseous, in gaseous state at room temperature. That means you have to use the hydrogen and oxygen in gaseous form inside the propellant tank, which is not practical because the propellant tank size will be huge. For example, even for a small rocket, the propellant tank size has to be of the order of kilometers height because hydrogen density is so small. So what do you have to do? If you want to use hydrogen and oxygen, you have to bring it down to liquid condition. Okay, when you bring it down to liquid condition, what will happen? Its volume will be reduced so that it can easily be stored in a tank. But there is a small problem. The problem is the hydrogen and oxygen will not be liquid unless the temperature is brought down to extremely small values, that is less than minus 150 degrees Celsius. Okay, less than minus 150 degrees Celsius is called the cryogenic range. So suppose I hope you are seeing this particular slide. So you are now at the room temperature in the middle. You can see the central graph kind of a thing. So when I reduce the temperature at 0 degrees Celsius, what happens? The water will freeze, and below minus 150, you call the cryogenic range, but oxygen will liquefy at minus 193 degrees Celsius. The hydrogen will liquefy only at minus 253 degrees Celsius. So extreme cold condition. So the hydrogen and oxygen has to be brought down to these extremely low temperature ranges, which are called cryogenic ranges, for them to function or for them to store. So, but the upside is, or the advantage is, you will get very good efficient engine. But the problem is you have to bring down the temperature to very, very, very low values, which is very difficult. Maintaining the temperature at low temperature is different. And inside the combustion chamber, again, the temperature will go to thousands of degrees Celsius. So it's very complicated technology. So this is what they call a cryogenic engine. So what is basically a cryogenic engine? A cryogenic engine is one which uses cryogenic propellant or propellants that has to be kept at temperatures in the cryogenic range. Typical examples are hydrogen and oxygen in liquid form. So it's very complicated technology to develop. And you may be aware, India already has developed this technology as part of GSLE Mark II. The same technology with the much powerful engines we are using for LVM-3 also. That is a rocket which was used yesterday for Chandrayaan launch. So this is another point which may be of interest to you. So in this picture, you are seeing a lot of rockets. India had a very, I should say, a history of rocket research and technology development lasting. We started in the early 60s with small sounding rockets. That is, it won't go to orbit, it may go to 100 kilometers and fall down. And we had the first successful launch vehicle developed called the SLV-3 launch vehicle. And then a series of other launch vehicles were developed, including the LVM-3 vehicle. But I have shown you there are different types of propellant stages. And then when you are talking about a rocket, it's not just propellant stages. You see this particular picture here on the right. This is a cross-section of the PSLV vehicle. So the PSLV is not just having fuel, one stage. It is having multiple stages, right? The first stage is having solid propellant stages. The second stage is having liquid propellant stages. Third stage is having solid, etc., etc. So depending upon the application, you will be building one stage over the other so that you will get the required velocity and the altitude. So this is how a typical launch vehicle works. So it will be having a combination of solid propellant stages, liquid propellant stages, etc. And the combination will be giving you high velocity and high altitude. So this is how this system functions. And you are familiar why these systems are basically used, because it is primarily to launch satellites. So what is the basic principle of a satellite? So this is explained, this particular pictorial representation is found in Isaac Newton's famous book Principia Mathematica Philosophiae Naturalis. Now, where he basically just gives a simple example. Suppose there is a small mass thrown from the top of a mountain. What will happen? It will just fall down. It will be going from, it will be having some velocity. You remember that it is thrown with very high velocity. So when it is thrown with very high velocity, it will be moving some distance, but it will be falling down because of the Earth's attraction. Now you will throw it with more velocity, it may again fall down at a certain distance. You throw it with more velocity, it may again fall down a certain distance. But if you throw with sufficient amount of velocity, it may again come back to that position. Or in other words, if you throw it with a critical velocity or above, it may keep on orbiting the Earth. It's a very simple way of explaining it. So if you want to make it effective, you have to throw it when outside the Earth's atmosphere. So you have to first take it to outside that Earth's atmosphere. Then you have to throw it, that is, you have to give a horizontal velocity, and then it will keeping on falling around the, it will keeping on moving around. So the same principle is used in the case of a satellite. Okay, when you are using it in the case of a satellite, the Earth is always trying to attract the satellite towards the Earth, which is given by the equation G(m1m) by r square. This is given by Newton. But if you want to balance that, there has to be a force in the opposite direction. That opposite direction force is given by the equation mv square by r, which is nothing but the centrifugal force. Okay, so the centrifugal force and centripetal force are balanced for a particular value of velocity. So this is how this systems function. And one more thing I think I will just show you, just to give a comparison. See, you have seen yesterday a GSLE Mark III LVM-3 launch. Sometimes people fail to fully comprehend what is the level of energy and power what we are dealing with. You might have seen it in the television. It may look very small, the rocket. But if I am just trying to give a comparison, see, for example, if I am asking a question, one GSLV Mark III rocket weighs, or the weight of an LVM-3 rocket is equivalent to how many number of elephants, or how many, if you put a balance, one side you are putting GSLV LVM-3, the other side you are putting, say, a certain number of elephants, how many number of elephants has to, or how you have to keep on putting elephants on one side to match it, right? So how many numbers will be required? So generally when we ask this question, people say 1, 2, 3, etc., etc. But the actual answer is something like more than 200. So LVM-3 vehicle is having a weight of around 630, 640 tons. And when you have that many number of mass, that is equivalent to the weight of more than 200. So what I'm trying to say is these are all extremely heavy, extremely complicated systems. And when you are having extremely complicated and extremely heavy systems, you require that much amount of power and energy to make it lifted off, right? So then only it will go to space. So when it is going to space, or when it is not even going to space, if it has, you just imagine something which is having the mass of more than 200 kilogram, 200 elephants, how difficult it will be to move it. Or in other words, how difficult it will be to accelerate to the velocity you want. So you can imagine what should be the power of the systems which are used to do that. So this is one simple way of explaining how much complicated these kind of technologies are. So this is basically about the launch vehicles. We have exactly taken 1 hour. So if you have any specific questions on this particular field, probably I can answer. Otherwise, it's up to the organizers to decide further what we have to do subsequently.
Sir, few still 10 minutes. We
Fine.
can.
No, then I can make use of the 10 minutes. If there are specific questions, then I will try to answer. I will try to, because I'm not fully aware, what is the level of students, or what exactly is their interest, or what exactly they know already, and what exactly they want to know.
Yes, sir, we can take
further.
questions.
Yeah.
Yeah. Okay. If any questions, please raise your hand, or
you can just type it in the chat box.
Chat box, so that we can. Krishna Murthy, sir, you want to ask the question? 1 minute, sir. I'll unmute you.
No, you can, because my audio is also not very clear, so it's better that if it is typed in the chat box.
Okay.
Okay. Meanwhile, while people are typing, we will also see why you want to have satellites. Because satellites are being used for various purposes, as you are aware. Many are used for communication. Many are used for Earth observation, weather satellite, navigation satellites. There are a lot of them, astronomical purposes. And there are one particular category of satellites, what we call as the geostationary satellites. So geostationary satellites are satellites which will be rotating around the Earth in the equatorial position, but it will be rotating with the same velocity of that of the Earth. Or in other words, because of that, from a particular point on the Earth, it may appear stationary. Okay, it may appear as a stationary. Okay, so this is what you call the geostationary satellite. So there are different types of satellites out there. Okay, I think some questions are being asked. I will try to answer that. Okay, I think one is a comment. Anglo-Mysore, these rockets are used by Hyder Ali and his son Tipu. I think I have covered that, right? So that actually, as it is pointed out, the original rocketry team, the rocket army, was initiated by Hyder Ali, which was of course inherited by his son Tipu Sultan. And then during the Srirangapatnam wars lasting 1792 to 1799, this has been used extensively. Now, another question is rocket an aircraft? Okay. By the definition of rocketry and rockets and aircrafts, if you see, the rocket basically means it uses a reactive propulsion. That's all. A rocket is using a reactive propulsion. That means it has to throw some mass out through one direction, and because of that, it has to move in the opposite direction, right? So this is what you call a rocket. And the question is, the rocket can be used as an aircraft? Yes, it's possible. In fact, there are many rocket-powered aircrafts were made in the 50s, 60s, etc. Even now, many are made for military and similar purposes. The rockets can be used for aircraft kind of purposes. That is, it doesn't have to be used to go from Earth to some outer space. You can use it like an aircraft. Okay, for example, there is some more interesting application is there. That is what we call a rocket assisted takeoff. Some of the aircrafts, like some of the fighter aircrafts, when it normally takes off, it takes a long runway. But in certain cases, when it is full with weapons, etc., and if the runway length is short, it has to have some additional thrust. And to get that additional thrust, what they will do, they will use additional rocket fixed onto that. So the aircraft will lift off with the rocket power, but it will not lift off vertically. It will be lifting off like a normal aircraft only, but the runway length will be less. And another classic example of a rocket powered aircraft, you may be familiar, that was called the Bell X-1 rocket, which was used by Captain Charles Yeager. That was the first aircraft to fly supersonic. So when I say aircraft, the aircraft basically means it is a vehicle which uses the wings for the lift. For the thrust, it can still use a rocket, right? So to answer your question, or to make the question's answer in a single line, yes, a rocket and aircrafts are basically, we use it in two different we generally use it in our common language as two different entities, but rocket means something which uses a reactive propulsion. Okay, and to go to outer space, you cannot go by an aircraft. It has to be a rocket, but aircrafts can be powered with rockets also. So that's the answer, right? Are there any nuclear fuel rockets? No, as on date, there are no nuclear fueled rockets are available. There are a lot of studies, renewed interest in that area. We had a lot of, or rather the world has seen a lot of studies in the 60s, both by the USSR, the Soviet Union, as well as the United States in the 60s. And the United States had a program called a NERVA, Nuclear Experimental Rocket Vehicle, where they have used hydrogen heated by the nuclear fission process and used, but due to obvious issues related to safety and mass, etc., they have not used it at that particular point of time. But now there is a renewed interest. Okay. Another question is a very good question. Difference between an engine going up and a lander engine to land. In terms of principles, both are identical. Both are liquid engine, or both are basically conventional rocket engines. But landing, it's a very, very complicated thing. So landing means you have to continuously adjust the thrust. A good landing engine will be having thrust varying capability. So this is what we call throttle ability. In rocket engine terms, these are called throttle ability. You might have, like an accelerator, whatever. Accelerator is also called a throttle in an automobile, right? So similarly, when the aircraft is coming to land, when the rocket is coming to land, then thrust has to be controlled very finely using a feedback mechanism. You have to get the information about your velocity, the descent rate, the altitude, etc., and accordingly, the rocket thrust has to be changed continuously. So that capability has to be there for a descending engine. Whereas in an ascending engine, throttling is not mandatory. Even without throttling, you can go, and the thrust variation is not generally done within a very, very small range. Okay, so that's the fundamental difference between lander and this. Okay, how to bring propellant to cryogenic engine? That's a good question. So again, you have to see how do you generally, when for a normal cooling operation, use a refrigerator, right? Refrigerator works on basic principles like vapor compression techniques, etc., etc., evaporation, etc. But here, when you are going to cryogenic temperature range, all these things will not work. So you have to use some special techniques or processes using, they are basically called Linde-Hampson methods, then adiabatic demagnetization. These kind of technologies, you have to use it to bring it down to cryogenic range. So certain things you can make use of some other fluid. Okay, you can in contact with some other liquid, but if you want to bring the temperature close to temperatures like 20 Kelvin, etc., you have to use special technique like the methods like the Linde-Hampson method, adiabatic demagnetization. There are a lot of special techniques are there. These are not just used in a common way. It is used by special companies. Okay, how accurately you locate the position of the rocket in the moon? It will be within the meters. The accuracy, this question can be understood in multiple ways. If you mean that the accuracy of a rocket is, the rocket will be having systems called the navigation, guidance, and control systems. Okay, so the navigation, guidance, and control basically will help you to identify your position, to gain the position and control the system. So altogether, we call it as a navigation, guidance, and control. So for that, we use a lot of technologies like, inertial navigation systems, satellite-based navigation systems, and so many other similar stars, sun sensors-based navigation. There are a lot of navigation systems. Based on that, the accuracies will be of the order of meters. Okay, in certain cases, in rough cases, it may be of the rough kilometers if you're talking about millions of kilometers. But if you are trying to land, these accuracies of the order of kilometers are not sufficient. So for that, you will be using special sensors like, special altimeters. By using a radar or some similar waves, you will exactly find what is altitude. Say at that particular point of time, your accuracy will be the order of centimeters. So depending upon the type of application, you will use different technologies, and basically by using the different technologies, you can get different levels of accuracies. That's how it is done. How do you maneuver the rocket from Earth? Okay, so this probably I will just try to answer using a small. I hope the slides are still visible.
Yes, sir.
Yeah. So one question is, how do you maneuver a rocket from Earth? So if you now, is it visible? I've tried to zoom the screen.
Yes, sir.
Okay, now you see the system carefully. There is a nozzle here. So if I am touching it here, now you can see the nozzle is moving, right? So this nozzle is moved by an actuator system in different directions. Can move in left and right. It can move across the paper surface, I mean the plane of the PC, etc., etc. So this is what I call gimballing of the nozzle. Okay, so what you are basically doing is you are controlling the direction of the thrust. So the rockets are controlled by controlling the direction of thrust. Okay, so by moving the direction of the nozzle in appropriate direction, you can maneuver the rocket from the Earth. But it cannot be randomly done. It will be done based on the trajectory of the rocket. So the trajectory of the rocket will be very clearly identified, will be decided. Based on that, using the same method what I mentioned, navigation, control, and guidance, and closed loop feedback system, you will be continuously adjusting the control systems such as the nozzle, gimbal, etc., and then appropriately by moving it, this will be controlled. So this is the same way by which the rocket goes to space also. Even when it goes to space, it has to, you might have observed, see the rocket goes so vertically, but if you want to orbit the Earth, it has to practically horizontal or parallel to the surface of the Earth. So this entire maneuvering is done by various methods, including we make use of gravity itself, we make use of this kind of gimbal technology, we make use of gyroscopic principles. So using that, this will be done. So there will be sensors on the computer, there will be sensors on the launch vehicle. Using that, we will find out what is our position and what should be the position and what should be the changes in the directions required. So that will be computed by the computer on board, and the computer will give the directions to the actuators, and actuators will rotate the nozzle engine so that it can move in that particular direction. Another question is, what will happen if the rocket failed to reach escape velocity of Earth's after? It's a very important question. The problem is, if the rocket fails to reach the escape velocity of the Earth after some time of takeoff, what will happen? As I told you, the rocket is having multiple stages. The initial stages will be completing its operation and it will be falling off. And if the rocket is failing to reach, if you mean satellites, the satellite is failing to reach the escape velocity, what will happen is it will be just rotating around the Earth only. It cannot escape the Earth. It will be revolving around the Earth. And after some time, due to aerodynamic drag, slowly its orbit will decay. And after some times, then what will happen? It may re-enter Earth's atmosphere and it may burn up. And if the satellite is very large, it may actually survive the re-entry and it may hit also. Okay. Now, next question is there any flying car aircraft? Yes, people have built a flying car aircraft. It's again, it's not something like a huge aircraft. That is, you can drive this car and at the same time you can convert that into an aircraft and fly. There are people who have built it not on a commercial basis, but there are some people who have built something which can be driven in the road. And then if you want to do that, you cannot just fly, you have to do some attachments. You had to arrange a wings onto that, you had to attach a propeller. There are a lot of things you have to do to convert that, but people have built it. But it has not found a huge market. People don't travel in that just like they are traveling car. What about maglev train? Is that also an aircraft? No. Maglev train is, there is something called magnetic levitation. Magnetic levitation is, there are one magnetic levitation train fully operational in China, that is between Shanghai airport to Shanghai city center, with some 30, 40, 50 close to kilometers are there. So they travel within 7 minutes or so. The maglev is already functional. Japan also has got some maglev trains operational within the city limit. Magnetic levitation means the train will be suspended above the trail by using a magnetic levitation. That is, by repelling magnet, it will be just lifting above the rail, and then using again a magnetic deflective force, it will be propelled forward. So it will be just moving as if it is moving in an air cushion. So because it is going in that fashion, the drag will be, the friction will be very, very less. So the maglev can travel comfortably in excess of 500 to 600 km per hour. Okay, so there are three countries which are they are doing a lot of research in magnetic levitation. One was Germany was doing it, Japan was doing it, China is doing it, but China has put a lot of money into that, and China is probably the leader. They already have an operating system, and Japanese also have made very high speed magnetic levitation in laboratories. Okay, large scale it's not operational, but in certain routes it's operational. Next question, is there a limit to mass of a rocket with chemical fuel? There is no limit. There is no, you cannot say there is a limit, but if the mass becomes above a particular value, the structure will become very, very complicated. No, the weight of the rocket will be very, very heavy. Some of the heaviest rocket people have ever made, there is a Saturn V rocket built by the United States in the 60s, which was used to take people to the moon. That was around 3,000 tons plus mass. The Soviet Union had an N1 rocket. That was the world's most powerful, heaviest rocket in that particular point of time. Then the Soviet Union again had a rocket called Energia rocket, which was again very, very heavy, 3,000 tons or so. But now, recently, there was a launch by SpaceX called the Spaceship One, Starship One or Spaceship One. So which was not successful, but that was the heaviest. So there is no limit to as it is put by that. But the rocket will become very, very heavy. The structure will become very, very large. It may be very difficult to make it. Okay, so that is a constraint. If you want to have a large number of mass, and if you provide equivalent powerful engines, it can function, but it will become very, very unwieldy. It is something like asking, what should be the size of your house? Is there a limit? There is no limit, but what will be the typical size you will build, even if you have enough money? There is a point in beyond building it beyond a point. So that's how it is. Whether any satellite launched rotate on its axis like moon as natural satellite revolves and rotates the Earth. No, that is it is not done. But generally, what we basically do is our geostationary satellites are like that only. Basically, when the geostationary satellite is launched, it rotates the Earth in 24 hours. In each 24 hours, the satellite rotates once. Okay, so what basically happens is the one face of the satellite will always be towards the Earth. Okay, so in that way, the geostationary satellites are like that only. But there is one difference is there. Geostationary satellites are having an antenna which is pointed towards the Earth, so that the communications can be done at all the times. Okay, so you can say that the moon case, the purpose of if I slightly extrapolate your question, you will see practically similar same surface of or same face of the moon always, not exactly same, more or less same face of the moon always, because of this what you call a tidal locking. Similar concept is used for geostationary satellite as well. The geostationary satellite also, you rotate, you in every 24 hours the satellite will also be rotating one. So in that way, it is identical to a kind of a tidal locking. Is there harm to environment from release of pollutants by rocket? Yes. If you ask me, is there any pollution because of a rocket? Yes, there is a pollution, but it is very, very small compared to other things. For example, an entire launch of one LVM-3 rocket, causes release of certain combustible product like carbon dioxide, hydrogen chloride or hydrochloric acid. These kind of things are left, but they are very, very small compared to other kind of pollutions what we have. And we, as you're aware, we have a rocket launch not on every day, maybe 10, 12 years numbers in a year. That may be the number what we do, but it creates pollution. There is no doubt on that. And that is why now one huge thrust is given to what you call green propellants. Okay, green propellants are, or let me also add, all rockets don't create pollution. For example, the cryogenic engine doesn't create any pollution at all. Why? Because the combustion product of cryogenic engine, that is hydrogen and oxygen, are the fuel and oxidizer. So the combustion product of fuel and oxidizer are nothing but water. So it is very clean. So cryogenic fuel and certain many other kinds of propellant, their pollution levels are practically zero, like this. But there are some which will create slightly comparatively higher level of pollution. So there is a range of you can grade them in different levels depending upon the type of pollutions. Some are polluting, some are not. But again, if you see the number of rockets and other kind of things, it is very, very less. Now, using NAVIC, can rocket be tracked? Yes. Using NAVIC, rockets can be tracked. Not just it can be tracked, these actually tracked. During the flight of a rocket, using NAVIC, we are continuously checking the rocket, its position using the navigation principles, and we are using it for our navigation. Electric propulsion, it is there. Electric propulsion, what you do is you ionize or you create charged particles from a gas like xenon, etc. You amplify, you accelerate it using an electric magnetic field, and then you throw it out through a nozzle. You will get a thrust, but the thrust is very, very small. So that is why it is not used for launch vehicles, but it is already used for launch satellites. What happens to expired satellites? The expired satellites, what as I've told earlier, a satellite which is expired, this is actually this will be falling down after a certain period of time. It all depends on where you are. Suppose if the satellite is in geostationary orbit, which is very, very high level, what will happen is, it will remain in orbit for a long time. Okay. You understood, no? Because it is at 36,000 kilometers. So what will happen is 36,000 kilometers away, this drag will be very, very less. When the drag is very less, what will happen? It will be remaining there for a long time. Whereas in low Earth orbit, the drag is relatively higher. And because it is relatively higher, it may re-enter at an earlier stage. So this is what is happening. So once it is expired, it can actually fall down as a debris. In certain other cases, if you know that in advance that the life is going to be expired, we deliberately push it to what you call a graveyard orbit. Okay. Comparison between LVM-3 and Falcon Heavy: size, weight, and thrust levels. LVM-3 and Falcon Heavy, Falcon Heavy is having more weight and more thrust. The Mark 3 LVM-3 is of the order of 650 tons or 660 tons I have mentioned, whereas Falcon Heavy, if I remember correctly, it is something almost double that mass, more than double the mass, 1,300 or 1,400. And Falcon Heavy is also having longer length. Okay, our LVM-3, if I remember correctly, is around 50 meters. The other one is around 70 meters. The thrust is also accordingly larger. Okay, what can be done to overcrowded the space debris? Will the rockets? No, rockets will not hit each other because there is no rockets are flying left and right. But satellites can hit each other. It's possible. There is something called the Kessler syndrome. If one satellite is hitting something else, it creates additional debris. It can again create more debris, like a chain reaction. No. It is possible nowadays because there is a huge number of satellites on the low Earth orbit. So there are a lot of actions are being taken, which of course you can see from Wikipedia or any other place. There's a lot of action. Due to lack of time, I'm unable to go to each and every one of them. There are a lot of actions being taken to tackle this space debris issue. Rockets will not hit each other because all the rockets are actually controlled. But once it is in space, if the rocket spin stages or some of the satellites which are non-functional, it can hit each other. It has happened already. The one Cosmos Russian rocket and other systems, Iridium satellite, they got collided. And some China, they have done some experiment also like that. So it is possible. So that's a very serious risk. Okay, rockets are protected from ions and radiations. The rockets are not very much protected from ions and radiations because the rockets has got a different function. It will go there and it will launch the satellite. But if you want to protect radiation of satellites, there are radiation protection shields are there. So there are radiation protection and radiation shield made of special chemicals. Some of them are called Nextel, and some special kind of chemicals are there. So they are actually covering the space stations and similar systems, and they will be protecting it from radiation. Because if humans are there, there is an acceptance level of ions, there is an accepted levels of radiations for each and everything. Yes, our Srinath sir has given a point that recently we have brought down Megatropics mission. Yeah, because Megatropic was very, very critical because that's a very heavy satellite. And suppose if you want to bring it down from somewhere from outer space, you have many options. One is you can deliberately bring it down and make it re-enter by controlling the re-entry path if you have control. And other thing is you can deliberately deboost the system in such a way that, or what I mean is you can start your re-entry in such a way that it will fall on certain locations on Earth where nobody is there. Okay, but if the satellite is smaller, then it will completely get burned up. Megatropic is a very good example of a very, very controlled re-entry, and that has been brought down very safely. Brought on the sense that is removed from the orbit very, very safely. And there is a point in Pacific Ocean, many of you may be knowing, that is called a Nemo point. Okay, that is far away from any inhabited places. So people generally try to bring this unused satellites and space stations into that. One classic example has been the way the Mir space station has been brought up, because Mir space station is a huge space station. So very precisely they have controlled it, they dismantled it on the go and finally landed on those areas without any harm. So this is very, very important. How rotation is access on geostationary cases achieved. The rotation of 24 hours rotation in a day is achieved by the initial orbit. Okay, so if you want to have the rotation in a particular time period, the simple thing what you have to control is you have to control the altitude. A geostationary satellite has to be at an altitude of around 35,780. You can roughly remember it as 36,000 kilometers. So if you are at an altitude of 36,000 kilometers, it will be having an orbital rotation period of 24 hours. But it will not be appearing stationary. So for that, what you have to do is you have to make the satellite inclination similar. I mean, I'll just try to show it. So this is the geostationary sun synchronous. Okay, so this is what we call an inclination. No? The satellites can be at different angles with respect to the equatorial plane. So when this is what we call an inclination. So if the inclination is 0, then it will be called an equatorial orbit, equatorial plane orbit. So when it is in the equatorial plane, then so this is hopefully this is also I mean it's visible to you. So these are the different types of orbits. In the first one, the equatorial orbit, the satellite rotates in the same plane as that of the equator, in the equator. So it will be just moving around the Earth as a fellow traveler. Whereas in an inclined orbit, the angle of the plane of the satellite orbital plane will be at an angle with respect to the equatorial plane. Okay, so one such case, or an extreme case of that, is what we call the polar orbit, where the satellite will be just moving with an inclination close to 90 degrees from pole to pole. So from pole to pole, if it moves, what basically happens, the Earth is rotating under it, and then the satellite is moving from top to bottom, so it can cover the entire globe. So this is used for remote sensing, right? I think that's fairly, we have come to the end of the questions. Anything else? I think one last question. Kindly give some guidance to get into ISRO. You mean to say that to visit ISRO, or you want to work? Can you be a little bit clear, Namrata? Get into ISRO basically means what exactly you meant? Work, fine. You want to, yeah. Okay, there are a lot of options. The first thing is, it all depends on which area you want to work. You can work in the science and related fields. You can work in the engineering stream. So the best thing is, if you are interested in doing science, you can pursue a course in physics, chemistry, or something similar. If you want to do engineering related activities in ISRO, you can get into a good engineering college and get a good degree with good marks. So it all depends on these two streams predominantly. There are a lot of other streams. You can work in administration, you can work in technical areas. There are a lot of activities in the technical area. What I mean by that is, there are people with diploma, there are people with ITA, fitting, electronics, soldering. There are a lot of activities. So the in a bottom line would be, whichever you are doing, you have to get with extremely good marks. Okay, as you are aware, that ISRO recruitment is very, very stringent, and the number of applicants for a post is very, very large. The ratio of how many number of people apply and how many can get into is very, very high. So you have to get into very good marks, and you have to study very well. You have to write a certain examination, the selection examination that you have to pass, and there will be an interview. And another option is, if you are doing your +1, +2, there is an option called Indian Institute of Space Science and Technology, which is in Trivandrum. So they have courses tuned for ISRO requirement. And if you study and if you get good marks and if you pass the appropriate exam, then also you can get into it. So if you want to give a single line answer, whichever we are doing, you have to get extremely good grades, marks, and you should be able to communicate your knowledge very effectively in an interview. That is very, very critical, not just for ISRO, to be precise. Any professional place you want to get in, and there is a lot of competition. So you have to do your studies very clearly, and more importantly, rather than just understanding and writing and reproducing in the examination, you have to really understand especially the physical concepts and systems. When you are studying, say, Newton law, when you are studying the mechanics, when you are studying, what I should say, the propulsion, thermal, whatever it is, electronics, whatever it is, you have to really understand the basic principles, and you have to understand, you have to really understand, not just, by heart or reproduce. So this is very critical, because in an interview, it's very easy to judge, as far as an interview body is concerned, whether you know something or you're just, by hearting something and when mentioning it further. So this way you have to really do that, and you have to develop a skill for communication. So unless you communicate it properly, whatever remains in your mind will be, will be remaining in your mind. It will never be understood properly, and people will be finding it difficult to gauge your capability. So these are the things you should work upon. That's all. So I think
Yes, sir, we can wind up here.
Yeah.
I think we answered all the questions in the chat box. Okay. If any question, you can text in our groups.
I'm
Tina, sir.
extremely thankful to Shiji Chandran sir for accepting in a short notice. That too, he is very busy because of the lunch. In fact, even I too am in office with the mission operations going on here. But Chandran, sir, it's a really pleasure to listen to you, and thank you so much for accepting and delivering the talk. Hope my voice is heard.
Yeah,
Yes, sir.
Yes. Thank you, sir. We don't have any problem in accepting any such, request or demand to communicate with our youngsters, and whatever little information we may have, sharing. As you very well know, Srinath sir will certainly be knowing. We always make it a point to interact with children, and whatever little help we can extend. I won't say help, some kind of general information what we may have, because we are working in an organization like ISRO. It's our duty to interact and respond to such demands. So if it has been useful, we are extremely happy. So you don't even have to say thanks or anything. This is part of our work, like what we do.
Right, sir. Noted, sir.
Yeah.
Okay. We are at the end of the session. Over to Divya.
Good afternoon, sir. This session was truly worthy, sir. I would like to express our heartfelt appreciation to our esteemed speaker for taking the time out of their busy schedule to share their expertise and knowledge with us. We are truly honored to have the privilege of hearing insights. Thank you very much, sir.
Thank you.
Thank you, Divya.
Yeah.
Thank you, Srijay, sir.
Okay.
Thank you very much.
Shall I leave?
Yes, sir. Yes, sir.
Okay.
We are ending.
Thank you.
Thank you,
Okay.
sir.
All the best to all the participants.